Okay, today the plan will be we are going to say goodbye to parsing, right? We're going to do a final bits for parsing. And then I'm going to go over this, hopefully not in so many detail, but at least to point to you so you can do the exercise later. And also for the exam, of course. And then starting from next week, we still got about 7 lectures, including the one I need to make up for you from last Wednesday, right? So from next week, we'll start talking about semantic analysis and also optimization. We'll try to do as much as possible. But the foundation should be parsing and scanning, of course. All right? Anyway, let's continue from last time. So last time, basically, let me just go to where we were. We were in the Goto procedure. Let me just go there very, very quickly. Okay, we're just going to point out to you how you can do the exercise. We went over the algorithm already. Basically, the Goto procedure, you want to find out where is the context over there. Okay, let me just show you what I have in my iPad. Okay, let me just point out to you the essence for Goto. Okay, you want to find out an item over there such that currently you're just before that you can match an X. And then what you will do is you're going to say the Goto should be I have matched the X already. Just move the bullet points, right? We're going to move that accordingly. However, there's a very important thing to note. At the end, whatever moved set you have accumulated, you want to calculate its closure. Don't forget that step. Otherwise, your resulting set would not be complete. It's like you have to calculate epsilon closure on that. Okay? And by the way, your assignment 3 is not due tonight. It's Friday. You know that, right? Okay, good. Just in case. Okay, that's about the Goto procedure. Why don't we just do one exercise very quickly to get you some idea. And then we'll move on to the next one. Okay, let's say this is the question, right? You're given a grammar, and you're given, let's say this is the CC0 item. Every CC item will be some set of LR1 items. Okay, so now what we want to do is we want to calculate for CC0, which is this set here, what would be the Goto set by matching a closing parenthesis. Okay, that's how we started with last time. But let's do a little bit more carefully. And I'll point to you what you really should watch out for. What you need to do now is to find out okay, first of all, the question is, we want to calculate the Goto for CC0, this set, by taking closing parenthesis. The critical thing is not necessarily every item in this source set. I call it a source. Not necessarily every item here will trigger some new item in the resulting states. Can you identify for me which one might trigger? So how about I number them very quickly? 1, 2, 3, 4, 5, 6, 7, 8, and 9. 3, 5, 7, and 9. So you're talking. Is your basis on the lookahead symbol? No, that's not the way to go. Okay, let me remind you. Okay, I'm just telling you the essence of calculating this, right? If you look at the algorithm again, all the item that we should identify is such that we are now in the context where matching X, which correspond to the input X over here, will be the next valid step, right? Okay, that'll be a hint to you. And now, what's the symbol? Yes, give me one moment. What will be the symbol we want to match? Closing parenthesis, ash. 6. Oh, just say it again, sorry. 6, 7, 8, 9. Everybody agree? For example, the reason that number 6 should be there is because you can see now we are in a context where the next one to match will be closing parenthesis, right? So that should be included. Similarly, we are now in this case, and that's also, the next one will be closing parenthesis, okay? You were not here last time. Are you okay with this? You're gonna follow up, good. Okay, so now let's say this. If we do put all these 4, first of all, so that will be the move set. Let me put them very, very quickly, okay? I would say pair produces this, pair, EOF. And then I also got pair produces this, pair, this, and just a different lookahead symbol, okay? And then number 8, that would be pair produces this, just different rule. And then EOF. And the last one would be pair produces this, So these are the ones that will trigger new item. I'll show you what the new item should look like. What we should do is we should move the dot over here after matching the symbol, right? So that should be the resulting Goto set. Well, so what I got to do, hopefully that will make sense to you. So it's actually after this, right? Oops. And the next question is, okay, so this will be the moved you can think about. So this is basically the moved set you will see in the algorithm. Now the question is, if you apply the closure that we spoke about last time, you may want to review it, okay? If we apply the closure to this set, are we going to get the same set, or do you think we're going to get something that's bigger? If you do believe there's going to be something bigger, can you tell me which one is going to trigger some new items? And before I do that, let me just be consistent with the numbering, right? This is 6, this is 7, this is 8, and this is 9. You think 8 and 9 will trigger new items for closure? Anybody? Before I point to you, back to the algorithm. Oh, yes, you see, the move set is only 6, 7, 8, 9. So now we're only focusing on these 4. So these 4 are for sure in the moved. But now we're calculating the closure of them. Are we going to get any new items when we apply closure? That's the question. Ashkan. For 6 and 7, okay, that's correct. But so now anybody want to explain why 6 and 7, or go a little bit more slowly, in this case? Guys, you see what we were doing here? Okay. Again, you only consider 6, 7, okay. You see, so this is the source, right? This is the source where you try to calculate the Goto. And in order to do that, you have to identify every item over there where the current context is right before you try to match the x. In this case, the x will just be closing parenthesis. In order to do that, we already identified these 4. So these 4 will be fixed already. And now what we want to do is the last step, which is to calculate the closure for this particular set of 4 elements, right? And what Ashkan correctly pointed out was, it turns out these 2 items over here are actually going to trigger new items in the closure, okay? The reason is, you can see, let me just remind you very quickly, right? I'll just point to you where you should look at, okay? If you look at the closure algorithm over there, okay, that we spoke about last time, when you review it, for closure, you have to see every such item where you're currently in a context where you're just right before to match some variable C. And then the way to add a new element into it is by thinking about what production you can make from C. For example, C produces gamma, right? That's a very quick review, okay? So what we should do now is go back there and see how we can do it, right? Let me go back there and let's see this. Just for example, you can see we are now over here, so we are now in the context right before we try to match pair, right? And now, in order to really get it work, what can pair produce? Pair can produce either this, or it can produce this. Agree? So we should apply these 2 rules to calculate the closure. So for those of you who might still be lost, maybe you didn't quite get the closure from last time, so review that. It'll be important for next Wednesday. Okay? But let me just, following this, what we should do, I'll just give you one example. In order to actually extend based on that, what I should do is, you can see what new item should I add, right? You can see this is the pair. Let me say I try to apply rule number 4, right? Rule number 4, by applying that, I know that it's going to be pair produces pair. Agree? And then the rule for closure tells us it should be in the beginning of that, right? But now, in order to figure out the item over here, we said you should calculate the first set of something, right? What should be the first set about? Well, remember delta and also A, right? So now you can think about, yeah, very good. At least you got some recollection. That's nice. So you can think about this guy over here is the delta that we talk about in the algorithm, right? And this guy, for example, EOF, is the A, the look ahead symbol. So what you should do, let me just do it aside, would be first off, basically delta will be this, followed by EOF. What would be the first set of this? Closing parenthesis, agree? Because that's a terminal, right? So in that case, all we need to do is put closing parenthesis over here. So that's the first item that will be triggered out, okay? So you can see if you want to calculate a go-to, the pink one, 6, 7, 8, and 9 is the first phase to calculate it, right? The green one I'm showing here is the second phase, where you have to calculate a closure to see what additional items you put in. Okay? Any questions? Think about it. For completeness, I'm going to write down just the final one, okay? And then for number 7 over here, also you can see currently we are here, and now we can match P potentially, right? So now you can see we can also we can also apply R5 as well. Okay, R5 once you apply that, you can also get a new item. Okay, for this guy over here, that would be your exercise. Okay, exercise for you to calculate it. And of course, if you see the textbook, you also they only tell you that you will just get 2 additional items from there, but they wouldn't tell you how exactly you calculate it. They assume you know how to. But I'll just show you one already. Okay, any questions? Okay. If you're completely lost, I would suggest maybe start reviewing the closure to begin with. Right, you will need it. Right. All right. After the go-to, let me give you the big picture. Okay, we still got 2 more algorithms to talk about, but they're not as tricky, right? They're actually in some way more intuitive. Okay, now the final one is to see the algorithm. The algorithm, I just want to tell you that this algorithm here, the way we construct it is very similar to the subset construction that we did previously, right? If you're given an NFA, how can you calculate the corresponding DFA? Right? You start with some initial, and then you try to keep calculating the reachable states. Okay? What I will do is, I'll show you very quickly the line, very quickly. Okay? And then we'll just show you the result of that. And then I'll tell you what you should really get prepared in the quiz or the exam. Right? The idea would be, I wouldn't really want you to construct a whole transition table. It's actually much more tedious than how you do it for subset construction. So what I might want you to do is to calculate just a tiny step for that, just to show me you know how to do it manually, just for a tiny entry. So I will assume you can do the rest as a whole as well. Okay, I'll show you that at the end. Okay, I just want to show you this. When you see the algorithm for building the canonical collection by CC, that's the acronym that was introduced last time. So given a grammar and given some Go production, so start variables is S, eventually we want to produce as S prime, right? Meaning that if you can match S prime, you can reduce back to S eventually. Okay? And then the output is going to be 2 things. Okay? We're going to calculate CC, and also we're going to calculate so-called transition function. Okay? Again, when you study this algorithm, try to link back to how the subset construction is done. Okay? So now let me mention quickly. You can think about CC0 is basically what we did last time. So you can think about this particular guy here, right? We talk about this special item. That's the initial state for your parser. So this is the start variable, and start variable can produce S. And in the beginning, we haven't matched anything. And if we can match eventually, and also EOF is the end of the input, that means we're done, right? So you can think about this calculation over here is to calculate the initial states CC0 to start with. Okay, this is the first one. And then based on this, you're going to calculate all the reachable ones. Okay? So you would say CC is simply initially just CC0, a singleton set, just in the beginning. And then you're just going to run a loop over here. Okay, I'm not going to go too many details. I'll just show you the critical step. You're basically going to keep expanding CC set over here until you cannot make it any bigger. That means you're done. Okay, That's pretty much like how you did it for the subset construction, because you pretty much continue until you have covered all the sets on your columns, right? Basically, you're going to go for every set over there. If that has not been processed, you will keep track of whether it's processed or not. And then you simply calculate some temp. You can think about the temp is the resulting set for the current one. So by applying Goto, you can think about Goto is really trying to take a transition. The current one is CCI that we're talking about. And then you're taking a particular symbol. And then by calculating Goto, you get to the temp. Thinking this way, CCI, and then you're trying to take a particular transition symbol by matching it. And then you're going to go to temp. Right? That's another CC set. So now the question is, you have to know whether this temp has been calculated previously. If it has been, you should not try to grow any further from that because it's already covered, right? If it has not been, you have to add it too, okay? So one thing to note, over here, you're trying to update this particular transition function to say from CCI, by taking X, you get to the temp, okay? That's really the algorithm, how you would do it. I'm not going to really trace it for you, but again, you don't need to memorize it. If you understand it, I'll give that to you if I need you to calculate anything. So now let me tell you what the outcome is. Okay, so this is the algorithm over here, and then I'm going to just to show you the question here. So if we say we want to calculate CC over here, I'm not going to ask you to calculate everything, right? I'm going to show you a particular step and also transition function. That's a typical question. So this is more or less the transition table you should get, right? It's pretty big. Again, such job in total should not be done manually, right? But since we're studying theory, I just want to make sure you can do a single step of that. That'll be enough. You don't need to calculate the whole thing. I just want to point out something to you so you can draw some connection when you study, right? It's not really complicated. You just need to be careful with the details. Okay, I'll show you two diagrams over here. Number one, you can see over here, if currently we are now in CC0, that's how we start with, right? Remember again, the CC0 is simply the closure of the initial item, right? That we talk about. That's always this a starting point. And then what we did last time was this particular one. We say starting from CC0, we actually try to calculate using this particular match, opening parenthesis, and then we'll get something. And that's actually called CC3. You have some naming convention over there, okay? And this, you can think about the way to calculate this is like this. By saying Goto, and then CC0, and then opening parenthesis. That's how you calculate it, right? That's how you draw the connection. In the quiz or in the exam, what I would do is like this, okay? To the maximum degree. I might say, for example, I will tell you what CC4 is, okay? And then I say now, calculate the Goto, for example, for this particular closing parenthesis. And then calculate and tell me what it should be. It could be empty, that's fine, but it could be something else. Okay, that's a question I expect you to answer. Just a single step for calculating some single entry. Okay, any question about this particular table here? Okay, I see everybody's paying attention, that's nice, but everybody also look a little bit quiet, right? Right? That's scary. Okay. Okay. Guys, if you're totally lost, that's fine. That means you got to review, right? I don't mind because it's complicated stuff. Coco, any question? Well, you're fine. You're fine. All right. So that's a table here. And then for your information, the transition table over here indeed is corresponding to this diagram over here, right? We are really trying to formulate the states of the parser, the bottom-up parser using some DFA, basically. First, it's non-deterministic. It's deterministic. Okay. I'll just show you one more connection here. The way to read this diagram, the way to see the correspondence between these two diagrams are, you can see CC0 by taking opening parentheses, we get to CC3. CC0, taking this, we get to CC3. Right? You'll see the correspondence there. Okay. You can imagine any bottom-up parser generator will be able to generate such thing for you, and then you can just use it at the runtime. Okay. If no question, I'll move on. And for your information here, you may actually want to try maybe a few entries in the table as preparation for either the quiz or the exam. Okay. Now I enumerate all the possible the entire canonical collection for this particular parser. Okay. In total, we got about 12 states, basically, right? Again, I wouldn't ask you to calculate all the 12, right? I'll give you one, give you a particular symbol to shift, and then you give me the corresponding one by using Goto, and of course, explain in details. Okay, so now the final algorithm to really go over, the final one, okay? Now, I want you to recall something very quickly, right? When we, maybe about a week ago, when we talk about basically, okay, let me go to this, that particular page first, and then I will shift. Give me just one moment over here. Remember maybe last week or 2 weeks ago, when I was tracing this particular algorithm, I told you that assume the action and go-to tables are actually existing, right? I said we worry about later how we can fill in the table. Now we can fill in the table. Given that we already calculated the transition table that I showed to you, and also we show you how you can calculate the CC, the canonical collection. Now you have the basis to fill in the table, okay? Again, it's an algorithm, so I will just show you a few entries. You can do the rest as an exercise, okay? The way to fill out the table, you can think about getting all the complete set of input. You got your grammar, you got your Go production, you got your canonical collection. Let's assume you have calculated already, right? And also you got a transition function, right? So you can think about number 3 and number 4. So these are the two outputs from building the canonical collection, okay? And then, so now the output will be the action and go-to tables, okay? I'll show you very quickly the step. The algorithm itself is not that complicated, right? Just got different cases to worry. Overall, you are going to say for every item, for every member in the CC set, and remember each member in the CC set is just another set, and you want to go for every item, okay? It's more like a nested loop. And then you're going to have basically different cases. By the way, it's a typo here. I should really get rid of this pause over here. I'm going to fix it when I post the slides tonight. You got several cases, and let me just remind you very quickly. When we look at the table before for parsing, right, for tracing, do you remember what S stands for? No, no. Shift. Either shift or reduce, right? Not states, okay? Be careful, right? S is shift. What about R? Reduce, right? Either shift or reduce. So now, in order to fill in the table, we should know an entry either is undefined, or it should be a shift, or it should be a reduce, or it should be a set. That's exactly what you will see in the algorithm, okay? So now we'll go back here, and then what I will do is, let me just tell you the cases. I'll just show you the code very quickly, and now I'll explain to you the pattern so you will understand. Either you can do a shift, or you can do a reduce, or you can do a set. Okay, I'm going to go over the pattern very quickly in just a moment, and I'll give you examples. And then for every item there, you also want to fill in the go-to table. Thinking this way. When you want to fill in the action table, each transition is actually a symbol. Okay, each transition. You can see over here, the transition here is either X, well, just some symbol, or it can be EOF. It's also a special symbol. When you fill in the go-to table, the transition is going to be a variable. Well, what I meant by was, you can see here, for the action table, okay? A little bit messy, but I'll try to be clear. You can see for both tables over here, the colon is simply the states, right? For the possible transition here, for action table, you can see they're all symbols, EOF, opening parenthesis, and closing parenthesis, right? For go-to table, they are variables, right? That's why, okay? You want to fill in both tables. Okay, and then, okay, you're going to fill it in. Let me explain very quickly about the pattern you should really recognize, and then I'll just do examples for each one of them, okay? And that'll be it. I'll rely on you to complete other entries in a similar way, okay? So now I will just go, also guys, our explanation over here for you when you study for that, okay? So let me just go to the example itself. Just bear with me. Just Switching to my iPad page. Okay, good. I already marked something, so I know what to show. Okay. So now let's say for the shift. Okay. Let me make it a little bit bigger. Okay. Basically, in order to do a shift, oh, too big. If I want to do a shift action, okay, I need to identify basically some item over there, such that, number one, you can see this item over here. Anybody can explain to me, if I give this to you, to explain what it means intuitively, this item here, the one I just highlighted in orange. Can anybody tell me what it means? Exactly. I say A produces beta, bullet points, X, gamma, comma, A. What does that really mean? Ms. Guff? You already matched beta? That's good.
So now you're going to check if X will be matched A.
Yes, the next one to match will be to really match an X. Right? Good. Exactly. Okay. So this item here, right, as Ms. Guff said, so beta here may or may not be epsilon. It depends on the particular rule, right? It may be epsilon, maybe. Doesn't have to be. Maybe epsilon. And this is the next symbol to match. Okay. In that case, that means we just want to shift. Okay. But what way should we shift to? It depends on the delta function that we just calculated previously, right? So now in this case, if currently, since currently we are talking about CCI, that's the current state we're talking about. So we want to see delta from CCI by shifting, by taking that transition called X, and then we want to see what the resulting state is, which is CCJ. So that's why you will see J over here. Okay, that's the overall structure for the algorithm. Okay, but let's see how we can apply this in the example. Okay, so that's just a shift. So now in this case, let's take a look. I just want to show you the one with the transition diagram. Might be easier for you. Okay, let's figure out how exactly we filled in this particular entry, which turns out to be a S6, right? Shift to state 6. How do we figure that out? Okay. So what that means is, if currently I'm now in state number 3, so that really corresponds to CC3, right? So now that means we are here. If we are currently here, okay, and then what we are trying to do is, if we try to do a particular symbol over here for parentheses, we know that the corresponding states would just be 6, right? You can think about the transition table already encodes what the Goto will actually return back to you, right? So now, in that way, we'll simply go to 6. So that's why shift and 6. That's how you calculate the shift, right? In order to fill in this entry here, of course, we assume you already got a transition table like down below, right? I might give that to you, or I might give that partially to you, right? Any question about the shift entry over here? Every entry in the table either be a shift, maybe a reduce, maybe a sept, or maybe blank, which means undefined. Okay? Any questions about this? Everybody is okay? Okay. Let's see the reduce very quickly. Okay. And then we'll do a sept. A sept is also very easy. Let's do the reduce. Okay. For the reduce, you got to be a little bit more careful over here. For reduce, we need to identify the item in the following format. Okay. Let me use a different color here. For reduce, we say if the current item has this particular format. Again, I want some intuition over here, right? Before we can try to see what the general rule should be. So Xi, you want to try? If I got an item like this, I say A produces beta bullet points, comma, A. What does that item really mean? What kind of parser state does it really indicate? Sorry, say it again. You're still trying to understand. That's fine. Anybody? Andre, go ahead. I agree we reached the end, but what have we matched so far? Beta, exactly. Good. Very good. So now what we have matched so far was the beta, and then now we're reaching the end. So now as long as the current word to consume will just be A, then we can reduce, right? Good. We want to find patterns like this. Okay. how can we find patterns like this? What you need to do is you want to go back to this particular page, right? Remember we already enumerated all the possible states, right? In some way you have to go over all of them to see which one can be matched. Okay? For example, I can just give you one example. How about this one particularly? Let's look at this one. Okay? I'm talking about CC8. Okay, if I'm talking about CC8, so that means I'm more interested about this particular entry over here. Okay, 8. That's what I'm interested in. Okay? So now what I want you to think about is, take a look at here. If you got this. Okay? This one is saying, over here, you can see we are now at the end of matching this. We're also at the end of matching this, right? And now we can potentially reduce back to the same variable, either pair or pair, the same variable. But be careful. In some cases, this will correspond to Abdul's question last time. What if we are now in a state where the two variables that we might reduce back to are different? You want to take a guess what that means? In this case, we're saying that the only possibility you can reduce back to will be just a pair, right? But what if they're different? Or let me put it this way. If in a single state, you're saying that it can either reduce to A or it can reduce to B. Isn't that ambiguous? Yeah. So that answers your question from last time. In this case, you will get ambiguity. Okay, well, we'll get there. We do have an example for you. I just want to mention that quickly. Okay, so now for this particular one, we know that if we are now in this particular CC number 8, because now we know one of the items over there is such that we're now in this particular state where we have matched everything already. Just by reading another EOF as the final input, we can reduce back to pair. Right? That's what we can do. And this pair over here, if you can see this particular rule. This particular rule, let me just double check for you. Okay, it's number 4. Okay, so now that's why what you will see over there is reduced to rule number 4. Okay? Reduced to rule number 4, which is the pair produces pair, just as a reference to you. Okay? The reduced part is a little bit indirect. You have to find out in the item where the bullet point is already at the end of the production rule and see what you can take. Okay? Okay, good. Finally, how can we fill in for accept? That one is actually rather easy. Okay? Let's see this. If the current format is such that S produces S prime, okay, S is simply the start variable. What that means is, for example, you can see that the initial one, sorry, this one here. Remember we talked about when we first introduced about LR1 item, we said either you have the initial states or you have the final states, right? Okay, so now this is the so-called final states, just as a quick review. So this is so-called the final states. That means we are now, oh, it's C11 here. Sorry, I might have circled the wrong thing. That should be something about EOF. Do I have it here? I don't. Did I miss it somewhere? Maybe it's actually not in, let me just find an item for you. So it would be list produces, can you see the EOF somewhere? I need to find it. Very quickly, remember last time when we talked about this particular one, let me just mention that quickly over here. So you will, right, there's an initial state that we talk about. It's right in the beginning, before the start matching the variable. And then we got another one over here. That's where I meant to go. This guy here, right? Over here. So you can see the desired final state would be go, produce its list, and the bullet point is right at the end. And then we are expecting EOF. Okay, good. Okay, that's about the set. Okay. So let me just go back here and just do one more. What about the go-to table over here? Go-to. How do we fill in the go-to table? In a very similar way. Okay. For the go-to table, you can see over here. Let's say again, you can use the transition diagram over there. Let's say I'm currently in state number 6, which is over here. And then if I take a variable as a transition, as I said, the difference between action table and the go-to table is, for action table, transition are symbols. Go-to table, the transitions are variables. So now if you take pair, so now it's like as if you take this particular transition, you should go to 9. So these are the two tables. Right? Filling in this particular, these two tables are really boils down to you want to identify patterns of the items that are in your CC. Okay? And what I can do potentially is to say, I wouldn't want you to fill in the whole table. This is one possible question. I can say now, I want given this particular table, let's say everything is blank. If I give you, let's say, current state is 1, and then if I try to take, let's say, closing parenthesis, what should be the corresponding entry? In this case, it will just tell me it's undefined, empty, right? Or it could be for the go-to table, if I say currently 0, take list, what should that be? Just 1, okay? Just want to figure out individual entry. Okay, okay, any questions about this? It's final bits of the parsing, but you know, it does deserve a little bit study of the details, right? That's why I want to cover still enough details. Any questions? Abdu, any questions for you before we talk about final detail, final topic for parsing? No, you're okay. Okay, I guess everybody needs to review. Go ahead.
You said that there won't be any backtracking here.
No, there won't be any backtracking, yes.
And the reason is because of, you said there will be ambiguity, but I don't know how that affects.
Okay. Coco's question was this. Let me try to clarify this. Good. We say that if we got a top-down parsing, right? You want to make sure the grammar you supply to the parser. First of all, it should be no left recursion, right? And also, they should be satisfied the LR1 property in order to be backtrack free. Okay. That one you know pretty well, right, from before. Okay, now let's talk about bottom-up parsing. You want to compare them, that's fine. Yeah. So now let's talk about bottom-up parsing. Okay. For the bottom-up parsing, the way we actually come up with the algorithm is a little differently. Okay. So now, first of all, so there is a skeleton. And the skeleton I'm talking about is like this. Okay, let me show you very quickly. The skeleton is basically like this guy here. Think about this algorithm over here is a skeleton, telling you that if you are given the actions and go to table, let's say, that's how you actually match them. Okay, that's a skeleton. Okay, let me go back. Okay, that's a skeleton, and then the next one will be skeleton, and also given the grammar. So now what you want to do the next step is to calculate, first of all, the LR1 items. Conceptually, right? You want to know about the L1 items. More importantly, you want to know what the canonical collection is. So these are all the possible states of. You can think about analogy of the NFA if you try to do a subset construction. Okay, so these are all the possible states. And then after this, what you will do is like this. You'll do something very similar to subset construction. First of all, you will calculate what's CC0, which is the closure of initial states. And then want to calculate everything that's reachable from CC0, so you'll get a transition table. I'm getting to your question, right? Transition table, and also, yeah, and also you will try to fill in the table. So now, let me just make a little bit more space for me. Once you got these two things, which we talked about last time, what you will do now is try to fill in the actions and also the go-to table. You can think about these two tables really represent deterministic behavior, because for every given state, you want to go to a particular action, there'll be a unique action you should take, which is the entry. So you never have to go to the backtrack to original. It doesn't exist. Such concept doesn't exist. How about that? In the bottom-up parsing. But now, given this idea here, what if your grammar is ambiguous? That's basically what Abdul was actually saying last time. Okay? Conceptually, it's very easy to think about, because if I have this, let's say this is my actions table, right? Somehow I'm in a particular state, let's say CC2, and then I'm trying to take a particular symbol. If I should really have only one option here to fill in the table, if I got potentially two possible actions I can do for this combination, that means it's ambiguous for me to see what you want to do. Okay? Let's see one example. That will be the last bits for parsing. Okay? Okay. Sorry, let me just go all the way to the last topic, which will not be too long. Discovering ambiguity. Okay? Remember this grammar here? This grammar was actually discussed right before we talk about the top-down parsing, right? And would you agree this grammar here is ambiguous, right? The so-called dangling else. Okay? I assume you know that's ambiguous. But now, the way we're going to show that is actually ambiguous is as follows. We try to calculate the CC. We try to calculate the transition table as before, like for the parenthesis grammar. And then the way we prove that it is ambiguous is when we try to fill in the table. We find that for a particular state, by taking a particular transition, there are two possible entries we might want to put in. That'll be ambiguous, roughly speaking. And if you got questions.
If that's true, this argument, even though it's exponential, it's still decidable. And if you can discover ambiguity, that goes against the proof of discovering ambiguity is not decidable.
I think, yeah, I agree with you. Yeah, I think overall, to really decide a grammar is whether it's ambiguous or not, it should be undecidable problem. I think for this, let me look it up. I don't want to say anything that's not right. Yeah, I do see your point. I'll look into it. Okay. I'm saying for this particular.
Say that it's not unambiguous, it says it's undecidable. Because this algorithm is definitely not polynomial, it's exponential.
That's true, because in the worst case, to calculate the CC, you have to go all the way to 2 to the power of the number of variables. But it might take forever, right? Let me look it up, and then let's see, have a better response. Okay. All right, so now let's take a look here. Again, we can calculate the CC, and then for now, again, I can just want you to calculate one of them, and also calculate transition function. Okay, very quickly, that will be, you can see, quite a complicated, even though it's a simple grammar. You can see the transition table is like this. But again, you should at least try two entries over there to try. Try one that will actually give you empty set. Try another one that will give you maybe some non-empty set. At least try as an exercise. Okay, overall, I'm just giving you all the answers over here, okay, for your reference. Overall, we're going to get basically, in total, up to CC14. So we got 15 different states. 15. Okay? Number one, just to tell you. Okay? But the way you calculate it is just the same as before. For that one, we don't have to spend time right now. And then, let's say for this particular state, okay? Let me just show you a little bit of notation over here, right? I got this diagram here from the textbook, okay? And then I'm going to shift to iPad over here, okay? They're just trying to save space. So when you see this guy here, it's really talking about two items. I'll put it here, right? It's really talking about statements produces if expression and then statements and then EOF. Another one, statements produces if expression and then statements else. Right? It's like these two items, right? Just as a convenience, right? If you really find a need in your calculation, I wouldn't mind if you put it that way. That's fine. It's from the textbook. Okay, but it's really talking about 2 items. And now let me just put the other 2 very quickly, right? The other 2 statements, okay, either E or F or that, right? Produces if expression and then statements. I'm not sure if you already see what the problem is, but I will lead you to that. That one can be E or F. And finally, I can say statements produces if expression and then the other one will be else. Okay, statements over here, else statements. That would be else. So these are the 4. So you can have, let's say, 1, 2, 3, and 4. For number 2, yes. Thank you. Okay. So we got 4, 1, 2, 3, 4. So there are problems in this combination. Let me lead you to that, okay? Stare at that for a moment. Think about how you can fill in table entry, okay? Think about in this way. In the corresponding table, that looks like this, right? Let's say for the action table, somewhere the column you have CC number 13, right? You just get 13 over here. And then you want to put some symbol over here, and then you want to put the corresponding entry over here, right? That's kind of the rough sketch, like how you can fill in the table. And there are some problems over here. Good, okay, good. Oh, no, we'll get there. You're getting there, yes. Okay, for those of you who have not seen it, that's okay. I'll lead you a little bit on the slides. But that one just to show you that you will encounter some problem in the sense that the single entry over here cannot store 2 alternative actions. If there are more than 1, then you're in trouble. It's ambiguous. So what I will do is I'm going to basically just give you this problem here. So now, according to these 4 items over here, what does it really mean if the next word to consume will be else? Exactly what Coco just observed. Anybody? Miska, can you see what's going on here? Okay, how about this? If I come back here, okay, basically what I'm asking is, if the word that we want to consume, the next one, is simply just an else, let's say, what are the possible actions? If anybody other than Ashkan would like to give it a try. Mahu, any thoughts? You don't have thoughts, okay. Miska, please. Hmm? You got 3 and 4? No, not quite. Okay, it might be nice to clarify this. You're saying it's 3 really applicable over here. But remember that actually, sorry, I'm okay. 3 is fine. It's only 3?
No, 4 is 1.
Are you sure?
Yeah.
Okay, so now what would be the idea here? Either you can, 3 and 4 is not the one to consider, I can tell you. You want to think about 2 potential actions that are just different. You're basically saying you can just shift, right? You just by shifting the else, you actually end up in the same state. So that's not a problem. Andre.
With 2, if we leave an else, then we're returning.
Exactly. So now you got either shift or reduce. That's really the issue, right? So now the way to see this is this, okay? Let me just highlight it, okay? You can see, for example, for 2 over here, okay, for 2, currently you're already at the end of the matching. So now if the next word to consume will just be else, so that means you can actually reduce back to the statement, right? That's a reduce operation. That's a reduce. On the other hand, for this particular guy over here, you will just get, basically, if you shift, you can actually just shift to the next one, right? So it's actually different operations. Okay. And so that's basically the answer, because you can either shift or reduce. Two alternatives. So that's so-called shift-reduce conflict. I'll try to maybe show you a little bit later on, maybe a little bit towards the end, after you study a little bit for the parser. Usually, when you try to put some grammar in the parser generator, if you have such conflict, it will actually show you exactly this kind of output. Okay, that's something we'll see later. Okay, any question about shift-reduce conflict? Basically, in the same states, by consuming the same word, you can either do shift or you can do reduce. Either way, right? So these are simply not something you can do at the same time, either shift or reduce. Okay. There is another one, and one just for your information. Later on, if you actually use some parser generator that's going to generate a bottom-up parser, shift-reduce conflict is something they have some heuristics to resolve. They will usually take the shift option rather than reduce. That's usually the heuristics. However, the next one is actually more fatal if you have it. Right? We don't really have, I don't have an example here for now, but just to explain the concept over here. Let's say we have in the same states, let's say the CCI, right? Just some element there. So now, can you see what's wrong over here in the same states? Andres, go ahead.
So we reach the end, so we're going to return. But for the first one, we're returning to A. For the second one, we're
Yep. The only thing I'll be picky about is reduce rather than return. Yeah, exactly, right? So now, exactly. So now I think maybe in some way this is easier to see. The previous one is that either you can do shift or reduce, but now both cases, because the look-ahead symbol is the same. If the current word you want to read is simply just A, which is matches look-ahead, in that case you can either reduce to A or you can reduce to B. So these are apparently two different operations, right? And then similar logic here, and then it was simply called reduce conflict. Okay? We okay? All right, so that would be the end of parsing, right? Yay! All right, good. But I would say again, since we are trying to study compiler course, we do some hands-on stuff for your assignments and projects. But in the lecture, we also got to cover some theory for parsing, right? You should know. Okay, any high-level question you have about parsing, anything, before I draw a closure on this? Everyone's okay?
Well, again, this is one of the performance questions, but you talked about how bottom-up and top-down have the same performance and after you done the initial steps. But the initial steps for top-down parsing seem more realistic to do with like computing first plus and all those things instead of
Because for the bottom-up parsing, because when you calculate CC, potentially can go exponential. Yes, I agree. But I think in practice, given the grammar you have, I don't have statistics for that. But in practice, for the grammar you want to actually do for your application, it may not take up to exponential exploration to actually find out all the entire set of CC. Yeah, assuming that, we are fine. Of course, in the worst case, you may have to go for exponential on calculating CC. That one I agree. Yes. Abdu. Of course, of course. Absolutely. The best way to do it is go back to that particular slide, okay? So guys, the question was, what's the difference between RR1 items versus CC, okay? Then you just go back to the slides and then we'll talk about it, okay? Okay, you want to pay more attention to this particular slides because that's more like a transition, from talking about LR1 items to CC, okay? You can think about LR1 items just all the possible ways to annotate your grammar to signal what are the possible parser states, but not necessarily every state will somehow be reachable in that sense, okay? So what we're doing is, I think the best analogy goes like this. Okay, again, just talk about it quickly. So you talk about LR1 items versus also CC collection, right? First of all, each member in CC is a subset of LR1 items. So think about in this way, right? Conceptually. Let's say I got LR1 items like this. 1, 2, 3, 4, and 5. Let's say I got 5 of them, right? And then let's say this is the initial one. Let's say this is potentially the final one, right? We can talk about initial and also final, okay? Now, our CC is going to be like a subset, right? The reason that we want to calculate CC is to really calculate how we can move from reachable subset to another reachable subset, right? So this could be a potential subset. So maybe that's simply just CC0, okay? CC0 over here. The corresponding DFA looks like this, CC0. And then by taking care of some shifting, so or transition, let's say, if I try to calculate, for example, Goto over here, and then I can say CC0, and then I try to do some shift on X, right? It can be opening parentheses or it can be closing parentheses. So what I would get, maybe just another set. For example, it could be this guy here, right? Let's say cover 3 items over here. Let's say this is CC1. So that means by taking this particular transition, I'm getting CC1. Okay, that's why we need a CC. You can think about it as all the reachable subsets of the LR1 items. Again, you want to think about LR1 items are all the NFA states, and CC would be the subset states of the LR1 items, which we use as the DFA states. Mm-hmm.
Also, like within that diagram, it looks like we have like one LR1 item more than one CC.
It's okay because it's a potential subset, right? I'm just saying you can think that's why we said over here in the slides. The way you define LR1 in the worst case, it will just be, so you can just see it's a subset of the power set of LR1 items, right? So maybe think about the power set concept over there. If you got trouble, speak to me, okay? Yeah. So that's why we argue that potentially your bottom-up parser might be very expensive to generate because the CC set could be exponential on the number of LR1 items. It could be. But depending on how large your grammar is, really depends. Okay? Guys, any more questions about this? Okay, so now for quiz number 4, next Wednesday, right? Okay. Next Wednesday, I'm going to cover basically just bottom-up parsing. Okay, I'll formally announce that in the forum. And then I'll give you some exercises this time, just to give you some idea why you should get prepared. Okay? And then, but I will still expect you to study them because it may not match exactly what's on the quiz, right? Don't expect that, okay? Any questions about this? All right. I would say I finished earlier today, maybe? And the quizzes, yes, I'll do that, yes. Okay, let me stop the recording. So definitely from next week, we got 7 more lectures, and then we'll start talking about semantic analysis, okay? Which will be a different perspective for the compiler.